So welcome everyone to CITA Colloquium. It's a great pleasure to have Connor Stone visiting us today from the University of Montreal. Connor got his PhD from Queen's University last year and moved to Montreal as a CITA National Fellow also last year, I guess?
September, yeah.
September. Welcome to CITA. I guess you'll be around hopefully multiple times, and we're looking forward to your talk.
So, thank you for inviting me. As you said, I just started as a National Fellow in September. This is my first postdoc and my first time actually coming to CITA in person and getting to meet all of you, which has been really great. And I hope to meet more of you because I'm staying the rest of today and tomorrow as well. So that should be fun. Today, I'm going to talk to you about score-based modeling in observational astronomy. If you don't know what that is, you will in 1 hour. So that's good. And before I get started in my talk, I'd just like to thank the people at Montreal. They've been really welcoming and they've shown me all sorts of really cool science like this score-based modeling stuff that I've been learning about since September. The team is actually quite a bit larger than this, but these are the people that I've been working with most closely. So I just wanted to thank them for welcoming me into their team. Now, for my PhD, I spent a lot of time putting together a compilation of galaxy surveys so that I could look at velocity information, so rotation curves for my galaxies as a function of radius in the galaxy, how quickly is it rotating, and matched with that photometry for a lot of these galaxies, over 1,500 of them, where I did basically isophote fitting. I could extract structural parameters about these galaxies, their size, their brightness, their color, all sorts of interesting properties, about 1,500 properties in total if you consider different variations, like computing them at different radii in the galaxies. And from these structural parameters about the galaxies, I can construct scaling relations, which span many orders of magnitude, as basically everything about galaxies spans many orders of magnitude. Once you have these scaling relations, you can do a lot of science and analysis with those. In my case, for my PhD, I looked at the scatter around scaling relations. So in this particular scaling relation called the radial acceleration relation, the scatter around the relation is sensitive to the model of dark matter in the universe between MOND or lambda CDM. And don't worry, lambda CDM is okay. So I did that for part of my PhD. And I also tried to work out a Bayesian framework for analyzing the scatter of these scaling relations. And I found that there was more than had previously been estimated in the literature. And so there was more diversity in the galaxy population than originally found. And all the while doing this, what I really want, because these are population studies looking at scatter, is I want as many observations as I can get my hands on. And you know what they say, careful what you wish for, because in astronomy, we're sort of entering a new era with lots of really exciting telescopes coming online, doing programs like the Rubin Observatory, which will be producing petabytes of data all the time. And it's not just a lot of data, it's really good data, right? So when we look at deep photometry, we realize that the universe is absolutely jam-packed with galaxies, which is what I study, but also stars. They're everywhere to the point that they're overlapping each other on our images. And so extracting the information about any one of these objects means having some understanding of the light coming at you from all of them in the area. So that adds to a certain complexity, but it's a good problem to have because it's deep data with lots of galaxies in it. A lot of movement has been discovering that lower mass galaxies are sensitive to really interesting processes that occur in galaxies. So we want to push to the low surface brightness regime where we get dwarf galaxies, where we get ultra diffuse galaxies. So that's an exciting direction that a lot of galaxy analysis has been taking. And we don't just have one good observatory coming online, we have a whole bunch of good observatories coming online, which means that we're going to have multi-band information about these objects, and synthesizing that in a meaningful way that gets us at all of the scientific information that's available in these observations is going to be quite a challenge to piece all of that data together. Further, you may have noticed in the JWST images and also other telescopes that are going to come online, like the Roman telescope, they have quite complicated PSFs. This one has like the 6-pointed diffraction spike, but at the same time, we have better modeling of the PSF than we've ever had before. So this is an opportunity for sophisticated tools to help us drive deeper than we've ever been able to before by understanding and modeling these PSFs to a really high level of precision. And of course, you always want to be Bayesian or in some way understand the posterior distribution, like your full uncertainty model of what's going on in your data. So all of these things sort of represent what I've been thinking a lot about lately, which is these good challenges that we have set up for us. These are going to present a lot of difficulty to process all of this data, but that's a good thing because we'll get lots of really cool science out of it. The JWST images really exemplify a lot of these things that I've been talking about. You can see in this that any object that you would want to analyze, if you wanted to say, understand this galaxy here, you want to understand something like the structural parameters that I was extracting in my PhD, the size of the galaxy, the color, the concentration of the light in that galaxy, all these properties that we can actually do science with. This image that you're looking at is just a giant matrix of pixel values. That doesn't really help us do any science. You need to then go one step further and get some reduced information about these galaxies to start studying their populations. But this galaxy here, there's a diffraction spike coming at it. There's a larger galaxy where, at least on my laptop, you can see it's spreading light all the way over onto this thing. So you kind of end up needing to model everything going on in this image before you can start to do your science and analysis on these galaxies. So the way that you go about doing that is generally for each galaxy, you pick some model or some way of representing it. This typically involves determining what its structure is going to look like. If you imagine all galaxies were circular face on, then projected onto the sky, they would form some sort of ellipse. You need some model to assign a brightness to each pixel, which often takes the form of something like a Sirsic profile, which as a function of radius in your galaxy moving out from the center, it can assign a brightness to your pixels. If this model is changing at a higher rate than your pixel scale, then you're going to need to like subdivide your pixels, integrate them, and really get a robust model of the surface brightness as a function of position in your image. Then the model parameters that were involved in constructing this can become your reduced data, the concentration, the size, the total luminosity of your object. So this is sort of applying these models for every object in your image is one way to extract the information that you need in order to go and do your science, like building up those scaling relations. At its core, what you're doing in order to get these model parameters is just a chi-squared optimization. So you've probably seen chi-squared before, but just to reiterate, because it's going to come up a few times, your pixel value that you've measured would go here, the uncertainty on your pixel is here, and your model, which assigns a brightness to every pixel, goes here. And so you just sum up for all of your pixels, and that is your chi-squared, which is just a negative log likelihood. And so you want to get a maximum likelihood, then you minimize this chi-squared. If you want to get a full posterior, then you need to do an MCMC in the chi-squared. So this is what is happening at the core of a lot of, yes? Cluster variance between pixels. So in principle, you could get something more complicated than just a standard deviation per pixel. This is assuming that every pixel is independent, which of course isn't correct. So you can take this further, and there is actually some work being done at Montreal about going beyond assuming a Gaussian for every pixel. I don't have that actually in my slides, but I do have extra slides if you want to talk about it later. So yeah, assuming that your pixels are Gaussian, this is the core thing that you're going to be dealing with as a baseline, and then all of your modeling goes on top of that. There are a huge variety of codes that have been developed to solve this problem from one angle or another. This is 40 years of development starting in 1985. and papers coming out right up until 2023. So a long literature of trying to extract information from images, because as I talked about at the beginning, it's very hard. There's a lot going on in these images, and trying to do this in a way that's robust and fast is sort of a tension that requires a lot of thought. And so a lot of thought has been put into this. Now, given how many different codes have been developed to solve this problem, you might think that we don't need another one. But I'm going to argue that we do. And it's because of a new development that's kind of coming from the machine learning world. And these are codes such as PyTorch. There's other ones like it, but what PyTorch provides you that none of the previous codes had access to is two sort of killer apps. One of them is you can write your code basically the same as regular Python with using NumPy, but in the background, it'll actually accelerate your code with GPU or CUDA code. And this is really powerful for image analysis because exactly what you want to do is what GPUs are ideal for, performing many operations, many simple operations on pixels over and over and over again. So there's a huge acceleration that you can get from GPUs, and the GPU world is continuing to grow with Moore's law, whereas CPUs tend to sort of level off lately. So there's a lot of like order of magnitude advantages you can get by moving your code over onto GPU. So that's one thing that PyTorch lets you do incredibly easily. And the other thing that it gives you access to is the computational graph. So through your code, every math operation that you apply to your pixels is tracked. And then at the end, when you get to a chi-squared, it can use the chain rule with this graph that it's constructed to work backwards to your original parameters and compute derivatives. This is really powerful in two ways. For one, it's exact up to your numerical precision of your computer. And two, it is super fast. Whereas finite differences is linear in the number of parameters that you want to compute a derivative for, this is constant. It requires one pass backwards. Basically, you do your forward pass, you do a backward pass, and you've got all of your derivatives at once. So it's much faster to give you derivatives for your parameters. So this opens up some algorithms like score-based modeling that weren't really available before. So using PyTorch, I did write my own image solving code. It's entirely written in Python and PyTorch. There's no compiled backends aside from PyTorch. And it's a like fully fledged astronomical image solver. It's got all of the models that you would normally use, and you sort of pile these on one at a time until you get a representation of everything that's going on in your image. This flowchart is just a condensed way to represent all the different models that you have access to. Because it's Python, it's really easy to get creative and invent new models. So that's what I've done here with like this warp model or the ray model. Like these aren't really in other codes just because I can be quite creative with it, and it's easy to add more if you want to. But anyway, this is a fully fledged image solver that is written in PyTorch. So it has GPU acceleration. In order to test what this really means in real terms, I threw a bunch of Sursic models, like I showed at the beginning, just randomly into an image, and then tried to optimize the parameters with Autoprove and with state-of-the-art like Galfit, which is really widely used. It's been around for decades, and it's compiled C code, so it's a pretty good reference in terms of speed. And if I compare Galfit, which is the brown, to Autoprove running on a GPU, as the problem gets bigger, it actually gets more powerful by relative comparison. So going all the way from 20 times faster up to 40 times faster in terms of how quickly it can get to that chi-squared minimum, which is a really cool, more than an order of magnitude speed up. So it sort of opens up the possibility to do things that you couldn't really have done before. That's what happens when you get an order of magnitude speed up. Yeah. So this test was just Sursic fits. Oh, yeah. This test was just with Sursic fits, but in principle, it translates to everything. And basically the more complicated your model, the better this should do by relative comparison, just because there's talk between the GPU and CPU that slows you down. So on smaller, simple models, it's only going to have a slight advantage. But when you get to really, really big models, then the talk back between the two devices sort of falls out as negligible overhead, and everything comes down to your pixel operations. I didn't even do any, yep.
To what extent can one use these automated unusual types of objects? For example, lens galaxies or
You are asking the perfect question. I will get to that later in my talk. Yeah, that is perfect. Like, we'll talk about lensing in particular.
Unexpected things? Or
We'll talk about unexpected things in lensing in particular. So perfect question. Yes.
Unexpected things, in addition to unexpected useful things, there are also a lot of unexpected not useful things like artifacts,
Love these questions. You're
effects coming from different kinds of instruments.
Yep.
So like, did the code handle that?
I will get there. So at this stage, Autoprof, think of it as a Galfit clone that is faster and has derivatives, and it's all Python, so you can interface with it really easily. So at this stage, artifacts and out of distribution things, you're not going to do particularly well on, because you have a strictly defined model for what the surface brightness can look like. But we will get there. All right. Just a little bit about what Autoprof can do. For example, in this case, I've got a spiral galaxy with a bar. And just by fitting these spline models, which I've sort of created because of the flexibility of writing everything in Python, it can actually recover this bar and spiral arm structure that you see there and get a spline model for the surface brightness of this galaxy really quite quickly. So there's some powerful stuff you can do there. It's also really fast, so you can work on gigantic models. In this case, I've got a cluster galaxy with a whole bunch of little galaxies overlapping it. This is a problem that comes up for anyone who's analyzing clusters. I ran source extractor just with default parameters to pick out all of the different objects. And then Autoprof takes it from there. It puts a little window around each object, comes up with its own initial parameters for the models, because I know that's a pain to do on your own. And then it optimizes those parameters and finds the chi-squared minimum for assigning Sursic models to these galaxies. You can see in the residuals that a Sursic model does not fully describe these, but it's still pretty good residuals, considering you can start to see the artifacts of like how the image was stacked up together. So you can work with really large models. I had to fight a lot of out of memory errors in order to get it to do this, but now it works. So I'm quite happy with that. There's other really neat things that you can do. Synthesizing information, as I mentioned, between multiple observatories. So this is Galax. I've got DESI and Unwise data here. So different PSF, different pixel scale, different 0 point, and you can actually synthesize this information. In this case, for the main galaxy, I used the structural parameters and shared them across bands, but the brightness varied from each band. You can also fit a PSF model at the same time. So each star in here has a fixed position, or not a fixed position, but the position is optimized between each band, but the standard deviation of the Gaussian, which I'm using to represent my PSF model, that is fit among all of the stars in this image. So this sort of like crosstalk between images and within images can all be handled now to arbitrary scale, which is really exciting. And you can extract a PSF model from your image while fitting everything going on. No more do you do cutouts and then try and median stack. You just get the model from your optimization. This is some cool stuff that Autoprof can do just because it was easy to play with the code. It's Python. What the PyTorch really gives me as like core advantages is one, the GPU, and two, the pretty much free derivatives. So you can actually do a version of a you can do a version of a markup chain Monte Carlo that takes advantage of derivative information. It's called the Hamiltonian Monte Carlo. and it allows you to scale up to really large models. So here I've got 15 overlapping statistics with a bunch of noise, and I can, in 6,000 steps of my MCMC, get a nice converged posterior for this model. I'm only showing you 14 of the parameters because there's 105 total, and you just wouldn't see anything if I tried to do the triangle, but they all kind of look like this, with like some parameters that are correlated, others that aren't. And in principle, with like a Metropolis Hastings MCMC, you just wouldn't even try something like this. It's too big in dimension space, and it would be really hard. It would never converge. But with the derivative information, you can take on much larger models and get Bayesian posteriors for them. So the way that I do this is called a Hamiltonian Monte Carlo. And the reason that it works, we can consider the curse of dimensionality. You may have heard about that before, but the idea is that as you scale up the number of dimensions, the amount of volume you have to explore grows exponentially. So if you've got one dimension, a regular Metropolis Hastings Monte Carlo makes a random step. So you've got a 50-50 chance of going the right way of like a higher likelihood. But you go to 2 dimensions, now there's 8 different directions you can go. 3 dimensions, there's 26. And you can imagine going up to 105 dimensions, you have no hope of taking a step in the right direction anymore. So you have to take really small steps, and it takes forever to converge. So wouldn't it be great if you just knew the right direction to go for increasing likelihood? And that's what you get with derivatives, but you do have to be careful to maintain detailed balance. So you're actually sampling from the posterior and not just finding a maximum likelihood optimal point. You do this with the score. So the log P of X here, that is your chi-squared. It's a negative log likelihood. And then you take the derivative with respect to your parameters, and that is called the score. And so that's why my presentation is named after score-based modeling in astronomy. So with this derivative information, you can actually much more powerfully explore an arbitrarily large parameter space. Basically, what you have access to, instead of the scalar field of a log likelihood that you have to step around randomly in order to explore, you have a vector field. If you had a starting point somewhere like here, instead of taking a random step, which half the time is going to move you off of your space, you can just evolve a point along this vector field until you're somewhere really far away in your parameter space, but still high likelihood. And doing this in a way that maintains detailed balance means you get MCMC samples that have extremely low autocorrelation, orders of magnitude lower autocorrelation, because you can move along really far in your log likelihood space. The actual mechanics of how this works involves treating your log likelihood as a potential and then using Hamiltonian dynamics. So your log likelihood is this. It's a probability distribution in your parameter space. And what you do is actually double the size of your parameter space by adding a momentum vector. And so you need some probability distribution for your momentum vector. The joint likelihood of that is now the space that you're going to explore, which looks just like a Hamiltonian with a kinetic term for your momentum and a potential term based off of your parameters. You can use Hamiltonian dynamics to evolve your particle in this potential and then just project away the momentum vector. And what you're left with is a new position vector that's moved really far in your parameter space. A little bit of care to maintain detailed balance and worrying about, you have to integrate along this trajectory. So each step of your MCMC chain takes longer to compute. You're not just evaluating at some parameter space, you're integrating along some path, but there are optimal choices to pick for that. And it still results in orders of magnitude drop in your autocorrelation between points. So it's more than worth it. And that is what Autoprof is doing here in order to get the posterior that you're looking at. Again, in 105 dimensions. This is really cool. And I just ran this last night. It's working. So yes.
When you say that you're using derivatives to try to follow a vector field to a better, more optimal set of parameters, sounds like gradient descent. Is there a difference between that and just?
There's a real connection between gradient descent, but instead gradient descent would be your Hamiltonian dynamics with zero momentum, because you just start your particle and then let it follow the gradient direction. Instead, what we do is we give it a kick. And so it starts to essentially like do an orbit. So if we happen to sample a zero momentum, then we will do gradient descent for a little while. But then the next iteration will sample another random momentum. And so we may get kicked up higher into our potential. Okay. Yeah. But it behaves the same way. Yes.
Why wouldn't you sorry why would you do gradient descent if you do Hamiltonian, aren't you just gonna shoot past the minimum?
Yes, exactly. But you want to do that. I'm interested not in the minimum here. I'm interested in the probability distribution. You need to get away from the minimum. And it turns out that with the right choice of momentum, you can kick yourself around this probability space in a way that explores it with detailed balance. And that's sort of the main. Yep.
Why are you propagating in high dimensional space? The higher dimensional space.
The higher dimension.
I understand.
Likely.
No, but when you have this high dimensional space that you're exploring,
Yeah.
why are you propagating a particle rather than a higher dimensional object like a membrane? Then you can cover more volume.
Why aren't you propagating a membrane? Is this something like a Gaussian process? A Gaussian process. Yeah. It's the same thing conceptually as like you just running a chain that evolves through your likelihood.
Right.
It's doing it in a more clever way. You can run multiple chains, and I guess if you're running multiple, and I guess you're kind of, if you're holding a membrane, you're kind of holding a membrane. But yeah, then it's a little like I think that would add a lot of complexity, and I don't know if that would get you the results any faster. We have more questions. Yes.
I actually have a question. Is there any advantage from HMC where you have a low dimensional distribution, but it's extremely degenerate, has potentially multimodality?
And there's a huge advantage there because if you have, say, like a weird banana, then the Hamiltonian has an understanding of that potential. And so each time you take a step, it's going to like evolve all the way to the other side of that banana, even though it's a curve or whatever shape it is. And so your autocorrelation just drops to zero because you're now going to move around that banana without needing to, like, something that you can do to accelerate a regular Metropolis Hastings is to, instead of sample from just a Gaussian in every dimension, you sample from a multivariate Gaussian that's aligned with your parameter space. Like here, you could, instead of sampling from a Gaussian, you could take a covariance matrix and know that you need to move longer in this direction than this direction when you take random samples. But in a more complicated space, it's even better to do the Hamiltonian Monte Carlo because it knows that shape and it follows it optimally. I'm not sure about that terminology. But yeah, it's even better than that in this scenario because you don't have to pick one sampling prior in order to do your HMC. So that's a really exciting thing that you can do with autoprof now for essentially arbitrarily large models. But this actually has the same problem that a regular MCMC has in terms of multimodal distributions. If you have a multimodal distribution with a large gap between them, you all probably know what happens here. You start your chain on some reasonable point, and then it's just going to sample from that point over and over again. And it's never going to, in a practical amount of time, make its way over to the other mode of your distribution. It turns out that there is a score-based modeling way to solve this problem too. And so in order to explain how this works, it's called diffusion models. And I'm going to turn the probability distribution sideways. So this is the two Gaussians here. If you imagine that you could sample from this distribution perfectly, then you could draw a bunch of points, which are what these lines are. And it's very easy to add noise, basically run a Brownian motion or a Wiener process on these particles and just cause them in parameter space to jitter all over the place. It's trivially easy to add noise to data. And when you do that, it actually collapses all the modes together into one giant Gaussian mode. And as long as you add enough noise, eventually all of your modes converge into one giant Gaussian. And a giant single Gaussian is very easy to sample from. That's not very hard. So what would be great is if there was some way to undo Brownian motion. If there was a reverse time Brownian motion process. And it turns out that there is. So that's what you're looking at here. I have taken these points, evolved them with Brownian motion until they got to this gigantic mode where they've lost all information of where they came from. And then I run a reverse time Brownian motion until they land back on the original distribution. And the way to do this is with the score. The background white haze that you're seeing is the probability distribution as a function of time. And the derivative of that is the score. And that's what you use in order to sort of like funnel the particles into where they need to go. The way this works operationally is called a stochastic differential equation. Some of you may be familiar with this, but essentially it's like a differential equation, but it's got a slightly different thing in that it has this term here where this noise is, instead of a small step in your parameter space that's like really regular, it's a small random kick to your parameter. And this is just a prescription for the noise as a function of time. This is your drift term, which you actually don't need to worry about. So if we ignore this, then your particle or your point in parameter space over time just gets a bunch of noise added to it until it's unrecognizable from what it was before. In this case, the author took an image of a little dog, slowly added noise until they got to an image of noise. And then they can go backwards. It's the same exact equation, except you need the score. If you can insert the score into this equation, the other terms are the same, and you can actually work your way backwards. What's really nice about this is that it scales up with the number of dimensions really, really well. So this is like 1,000 dimensions, over 1,000 dimensions here, because it's an image. And you can go from pure noise all the way back to some probability distribution. In this case, dogs, or images of dogs, really. So this is a really powerful technique. In this case, they're using machine learning to represent the score here, the probability distribution. And if you do this for galaxies, it also works. So you can just as easily construct images of galaxies using this score-based model. And basically, you start from an image of pure noise, and you use the score as learned by a machine learning algorithm to slowly drive yourself down into the like manifold of parameter space where images of galaxies live, which is extremely multimodal, but it's learned how to do that. And we know that like mathematically, it's covering all of these modes. Not all of these are actually simulated. So half of them are real and half of them are simulated. There's no way to tell the difference. Feel free to pick two that you think are definitely simulated. And then I'm going to put an orange box around all of the fake ones. And here we go. So about half of you were wrong. So yeah, the orange box ones are the ones that were sort of simulated by this diffusion process. And it's really cool and a fun party trick to generate images of galaxies that are entirely indistinguishable from other images of galaxies. By the way, the training set that they used for this was the probe sample that I put together during my PhD that I mentioned at the beginning of the talk. And Mike sort of took all of them and made his own diffusion model here. This is really cool, but what good is it to just be able to draw images of galaxies from noise, right? Like we can use telescopes to get images of galaxies. So we don't really need a way to produce random images of galaxies. But it turns out that this is extraordinarily powerful for solving so many different problems in astronomy. And I'm going to explain why. So Bayesian analysis, Bayes' theorem. This is what you want. This is always what you want, the posterior, the probability distribution over your parameters given some constraining data. Here is a likelihood. We know how to define this, and it's in most cases a chi-squared, some like difference between your model and the data that you've got. The prior here is where things can get tricky. Defining a prior over galaxies is really hard. So usually what people do is they pick some analytic prior that is relatively simple. In the case of autoprof, I'm essentially forcing this prior to be Sursic models or something along those lines. In some analysis, people will even go as far as to say, I want a flat prior. I want my data to tell me everything. And so I don't want this to influence my results at all. Or you may say, I want a Gaussian prior. Like the issue is if you have a flat prior, that in principle allows all images equally likely. But we have seen galaxies before, so we know that these aren't galaxies. I mean, I hope you know that these aren't galaxies. These are just fun random images from the internet. So a flat prior is a terrible choice for galaxies. Similarly, a Gaussian prior is a terrible choice for galaxies, but a good choice in some other scenarios. So you want to pick the right prior for the job that you're doing. And there is, in fact, a whole class of problems. Oh, right, sorry. First thing, you got to change Bayes' theorem around a little bit in order to do your score-based modeling with this. So you just take the log of Bayes' theorem and then take the derivative of Bayes' theorem. And what you get is the score of your posterior, the score of your likelihood, and the score of your prior. This is what a machine learning algorithm can learn. This is exactly the term that we were using in order to generate random images of galaxies. We were essentially drawing from the prior of all images of galaxies. But now in this framework, we can use that as a prior along with our model of what's going on to drive a likelihood that's determined by some data. So there's a whole class of problems called ill-posed inverse problems where this is absolutely essential. In, say, PSF deconvolution, you have blurred your image with some PSF, and it's an ill-posed inverse problem, meaning that you have truly lost information about that image. In Fourier space, it's a multiplication in order to convolve, and essentially you've taken a bunch of your frequencies in Fourier space and multiplied them by 0. You have no information there. As soon as you throw on noise, especially, like you are in trouble. Like there's nothing that you can do in order to fill in those frequencies with a more clever algorithm. There's no clever way to construct your code or your likelihood in general in order to recover what happened underneath that convolution. But you can, in principle, get a posterior, a sample of all possible images that are consistent with your data if you have the right prior. And ill-posed inverse problems require that you have a good prior. Anyone who's played around with PSF deconvolution has probably tried just dividing your PSF in FFT space, and what you get is a total mess. It's you get ringing and other artifacts, and a lot of that is because you're essentially imposing a flat prior that allows all possible images to exist. You don't want to do that in these classes of problems. So the solution is to get a good prior. In this case, a diffusion model that allows us to represent what these galaxies could look like, the prior of all possible galaxies, and then inform it by what data we do have. So I'm going to show you an example, thank you for the question, using strong gravitational lensing, where we have our prior here defined by this diffusion model. This is just all possible images of galaxies right here. Right here is our likelihood. This is entirely analytically defined. So for lensing, what happens is you have some galaxy in the background. It gets warped by your mass model, And what you get in the end for your telescope is an image that kind of looks like this. The object has been bent and twisted around. Any noise or convolution or like PSF blurring in your image gets applied onto this. And what you have is definitely a lot of information, but also definitely some information has been entirely erased. So this is an ill-posed inverse problem. We would like to recover the posterior distribution of all galaxies that are consistent with our observation right here. That would be the ideal scenario. So here we can set up, this is the real galaxy. We have a lens model and use that to warp our image and then apply some noise onto that. So we are now in the ill-posed inverse problem regime where all we have to look at is this noisy warped image of a galaxy. And we want to get back to this as best we can. And even better, we want to get a full posterior of what that could be. And so here we run our diffusion model. This is what the, this is a sample from the posterior. This is what the diffusion model comes up with. When you warp it with the lens model, you get this. Basically, the difference between these two squared is your chi-squared, and that's our likelihood. So we were using this difference with that, that's our likelihood, and then the diffusion model was constructing this. As I said, we want the posterior, so we should draw many samples of what this galaxy could look like. And once you have a collection of like a few hundred draws from the posterior, you have a way that you can like probe what information is actually available in here. And this is what you get when you take, say, the standard deviation of all of your posterior samples. Where the standard deviation is low, these black areas, your results are entirely driven by the likelihood. There is enough data in here to constrain those pixels really well for your reconstructed image. But as you move further and further out, the variance increases until you're at the edges where essentially the prior gets to hallucinate whatever it wants. But you can probe that and understand exactly what it is that your data is driving for you versus what is just being filled in by your prior. So this is the optimal way to analyze this kind of problem. This is full Bayesian analysis. It's like a whole different paradigm for machine learning. Oh, yes.
I just had a question about the likelihood. You said that you're doing a chi-square minimization that is going to put a Gaussian assumption on your errors. Is that something that would be a problem?
Good question. So that is putting a Gaussian distribution on essentially the pixel errors. Essentially what we're assuming is that we've collected enough light that the Poisson statistics are basically equivalent to Gaussian statistics in terms of how much noise was added to each pixel. There are ways to have more complicated noise, but in this case, the point was just sort of to prove that it worked, and so they just used that. You can define the likelihood however you like. So if you want a more complicated model, if you want to use Poisson statistics instead of chi-squared, all of that likelihood stuff, all of the lensing, the machine learning algorithm hasn't learned any of that. So that's analytic. You can add that in however you like. You can also blur this with a PSF. You could like cut out some pixels because a satellite went through your image and you can mask it. It doesn't matter because you're the one defining the likelihood analytically. The machine learning algorithm doesn't need to be retrained for all of these scenarios. All it's doing is guiding you to galaxies and not all possible images. So yes, you can totally take care of that if you want, but we did not in this case. All right, can we trust it? What if we have something out of distribution? Like we want to do science with these. So if we see a galaxy that we've never seen before that wasn't in our prior, can the data actually tell us what that is? And it can. So in this case, they took a 7, way outside of the distribution of anything the machine learning algorithm had seen before. And then we ran the diffusion model on it with very low noise. And if you have good data, your good data is constraining. So you get out what you put in. Basically, in principle, your prior has fat tails, it allows for a lot of variation. And if your data is really strong, then you'll get out what you put in. You can get out of distribution samples. But as proper Bayesians, as the noise gets higher, we start to draw more and more from our prior. These are just individual examples. If we redrew more examples, these would be totally different because the data isn't constraining that. So we get to fill it in with whatever we want, as long as it kind of looks like a galaxy. This is proper Bayesian statistics going on right here. This is perfect. And I should also mention that this in particular, this paper was done by a PhD student in the group at Montreal. And he did a really great job with this. So I definitely wanted to sort of give him credit. That's Alex. So yeah, this is some really cool stuff that we can do with these diffusion models. And it really comes down to just proper Bayesian statistics when you have the right prior. We're no longer in the regime where we have to sort of come up with regularization terms or approximations because those are all just attempts at a reasonable prior. Now we have the right prior. It's perfect. But what's the catch? Well, it's slow. I'm used to thinking of machine learning as a fast way to get an approximation. Now it's a slow way to do science better than we were doing before. So we no longer get the results in microseconds. It takes like half an hour to draw each of those examples that you saw while using a GPU, which is really fast. So it's not fast anymore, but it's all score-based, which means it integrates really well with autoprof. So something really complicated like the lens here, we can recover with the diffusion model. We can throw autoprof at all the little simple things going on in the image or the sky background, whatever. And because autoprof is score-based, it can keep up with these diffusion models and sort of fill out the easy stuff. So these two codes can integrate really well with each other. And that's the connection to autoprof. So yeah, all of these ill-posed inverse problems can now essentially be solved by this kind of technique. We're actually going to be getting at a whole bunch of these quite soon. So watch arXiv, because we're gonna be publishing a way to do all sorts of these kinds of problems with these diffusion models. Star formation history, interferometry, they're going to be a little while longer, but we are planning to work on that. In fact, in order to do it, you need differentiable codes where you can propagate derivatives through. So autoprof is covering like image modeling. That's my baby. That's the one that I've been working on the most. Gravitational lensing, we have a code called caustic, which will be out soon, which can handle all sorts of gravitational lensing configurations and propagate derivatives through it. And coming soon, we'll be working on SED modeling in a way that it propagates derivatives. So with that, we've got all sorts of really amazing science that we can do. In particular, my long-term project for my postdoc, I'm going to be analyzing the dark matter distribution in galaxies because with lensing, we're sensitive to the total mass distribution. With a differentiable SED modeling code, we could subtract away the baryons essentially and get at a full posterior of the dark matter distribution for the lensing galaxy in this particular scenario. So there's some really cool work that we can do with that as we build up these tools. So yeah, I'd like to thank you all for listening and I'll take questions.
Thanks a lot for the wonderful talk. Any more questions?
Slow, right? Because it's such high dimension. High dimension.
Yeah, it's high dimension. Kind of have to like slowly work your way. It's like annealing. So you have to slowly work your way down to the true distribution. So in this case, you have to evaluate your neural network 8,000 times in order to make your way down to the true prior in a way that doesn't fall off the rails essentially. And there's also like approximations along, there's details that I haven't included in here. In principle, at the high temperature point where it's a giant Gaussian, that's analytically perfect. At the low temperature point where it's our prior, that's analytically perfect. But in between them, there are some approximations that are made. So you have to go a little extra slowly in order to make it down to the right probability distribution at the end point. So sort of an area of extra work that we're doing as well.
So your model is relatively simple that you're fitting at the moment. So there must be redundant information in the full image. Is sort of compression going to be useful here to speed it up?
So there's lots of ways that you can speed it up. Because this is a stochastic differential equation, there is actually an ordinary differential equation that is equivalent to this in principle, if you're getting everything right, which means that in principle, you can use like a Runge-Kutta ODE solver and move through your space super fast, but you have to get it perfectly right in order to do that. And it's hard to do in over 1,000 dimensions. So they use the stochastic differential equation to sort of smooth out any errors that could happen along the way so that you land on the right probability distribution at the end. So yeah, in principle, there are ways to speed this up quite considerably. There are ways that you could potentially reduce the size of the problem that you're trying to deal with in order to speed it up. Like there's lots of ideas. This paper came out in November, so yeah, it's still definitely a work in progress. Yes.
So picking one particular image could take a really long time to do. But suppose you already knew a lot of information about that image. Say you knew almost the entire image, but then you perturbed, say, one object. Would it be able to just very quickly address the change that has happened to that object? Or would it be essentially starting from the beginning to try to fit everything again?
So every time you want to draw a sample, you have to start from the beginning. But if you had everything here modeled and you just really cared about that little point here, you could in principle fix everything and just run a diffusion model on that. But then you wouldn't really be taking advantage of the full power of what you can do with this and getting a posterior that includes the interaction terms between all of these different things, right? Because if this gets brighter, this needs to get darker, which means this needs to get brighter, and like it propagates through in principle.
A transient and everything else.
In principle.
Everything else makes sense.
And because it's stable, and because you define the like on your own purely analytically, you can already do that with this kind of algorithm if you have the code that can keep track of all that bookkeeping.
A related question is, can you incorporate time delays in your lensing inverse?
So time delays is something that we're working on in the, I don't know, is this working? Oops. In the, okay. So in the codes that we're working on, the caustic code that handles gravitational lensing, time delay is sort of an issue on the GitHub right now, is getting that to work. But the thing is, propagating your time delays is again an analytic part of your likelihood. So as long as you have the code for it, the diffusion model will keep up, because all it's telling you is what your galaxy should look like. It doesn't handle anything from here to here.
Does the inverse problem become well posed if you had, say, the whole image was changing and you had time information for each pixel?
Had a light curve for everything. Had a light curve for every. I don't think it's ever well posed in real data, because you still have like your PSF blurring your image. You still have that noise, but definitely like one thing that we are working on in the group is to look at multiply lensed AGNs and sort of extract as much, all of the information that's available to us in a light curve from that. But it's hard to do. And it's hard to even write the code that can do the analysis, and then getting the derivatives, integrating it in with this is another step. Yeah, in the back.
Thank you for the great talk. My question was about, you use the diffusion model, like kind of like a neural like STE, to learn the prior in some way. Why couldn't you do that directly to learn the posterior and somehow include the errors into the Brownian motion?
Could you a SDE on the posterior? Well, so the way that you get your posterior is by evaluating your SDE under the constraints of the current data that you have. So in a sense, you are doing that, but you don't have to relearn anything in order to do that. Although I say that, technically, all of these problems are in a certain formulation linear problems. And if you want to do nonlinear problems, then the math that we used in order to do this doesn't work out analytically perfect. And so there are approximations that you can get that are like a predictor and then corrector term. And that corrector you have to learn on each individual case. It's complicated, but if you want to go to nonlinear problems, then you do need, there is some extra work that you need to do in order to get there. And it's sort of along the lines of learning something about every observation that you have. It's even slower.
Thank you.
I think you had a question, yeah.
Are you on me now?
Is someone online with a question?
I do. I thought I had my hand up, but I can't actually see the hand. Is it okay, or is somebody else asking a question?
Okay, I can ask. There are 105 parameters in your example fitting. So I wonder if the number of the parameter is fixed, how do you know like how many how do you know the dimension of the parameter space? Say if there are clumps, nuclei in the galaxies, is it like decoupled from?
You referring to this?
Yeah. So I wonder if like how do you know the dimension of the parameter space that you want to fix?
In this case, I created the image, so
I know. So you know there are like several thoughts, but
in cases like this, in order to know how many models or how many galaxies you have, you use a segmentation map. So this breaks up your image and tells you how many galaxies there are in this particular image.
it's like a catalog input.
You need a catalog, yeah. You need
It's like a loads of brightness galaxies or like I don't know, global clusters around galaxies. So that will possibly be missed in the output.
if Autoprobe just essentially does optimization. So if you don't tell it everything that's in there, you can get worse results. This is true for all image solving codes. So it's a limitation, but it's a limitation that you have to have. There's no way to get around it. Online question?
Yeah, so a great talk.
Thank you.
The Hamiltonian Monte Carlo, there is a prior version, which was a Langevin approach. The Hamiltonian has some benefits, but instead of Hamiltonian, if you can do it, Hamilton-Jacobi is a very nice way to go. And what that requires, though, is that you get Hamilton's principal function. Here, your potential is basically like an entropy. It's minus log rho. And do you know what Hamilton's principal function would look like, and what advantages that would have in treating this problem, in the sense that that is like a gradient flow?
So first thing, you mentioned Langevin dynamics. Langevin
Yeah, that
like
was sort of the precursor to the full-on Hamilton approach.
Yeah. So Hamilton is like a single step, or sorry, Langevin is like a single step in the Hamiltonian, and
That's
the
right.
Hamiltonian dynamics integrates this for many steps until you get to some stopping criteria. The other problem that you mentioned, I'm not familiar with. Does this require something like a Jacobian in the image instead of just a derivative?
No. And the critical problem in using Hamilton-Jacobi is actually finding the form of the Hamilton's principal function. It's a function of basically your starting parameter and your final parameter, and it follows the flow. This is fundamental in a quantum mechanical setting. And I was just wondering if it's closely related to that effective entropy that you're using for your potential for the gradient flow of momentum, if you like to use that terminology.
I don't know.
I don't think this has been used, but I'm just wondering why not, because we use it all the time, for example, in inflation.
I guess I should look into that, because if there's a better option that has the same primary mechanics, then I should definitely take advantage.
And there's another ingredient here, which is mainly because she's a very good friend of mine. Eva Silverstein has been using what was called Dirac-Born-Infeld form of the action. And that involves a correction, which is more relativistically correct, so that you aren't using non-relativistic flows. You're putting in what is in effect a finite velocity, so it can't flow too fast. This is something which I know that Eva is working with Euro Seljak for doing some of his attempts to do forward modeling for cosmic web type inferences. I don't know, have you gotten into that at all?
I haven't gotten into Hamilton-Jacobi stuff at all.
No,
but
this isn't Hamilton-Jacobi. This is basically a modified form of the action from which one is deriving the equation of motion.
Okay. So
And
the
the advantage it has is that it means that it controls the flow rate as you're going down, either trying to find minima or sampling other things, which has a lot to be said for it. And in fact, it's probably useful for every gradient flow to put a speed limit.
as long as it still maintains detailed balance, which is really important. And I'd have to look that up.
Okay, with that, I'd like to close here, but if you want to discuss more with Connor, I would invite you to sign up for a meeting with him on the spreadsheet I sent around earlier. Let's thank Connor again.